Now in this lesson we'll continue on with our finite difference approximation topic, but we'll do some examples and then look at a technique for extending the accuracy of these types of approximations for derivatives. One precaution though, when you're using Python scripts to do these approximations, it's really a good idea to use 64-bit arithmetic in this case because of those error terms that we have, and so precision can be very important here. So as far as Python is concerned, when you're creating arrays and, for example, using NumPy to approximate these functions, then you probably want to use the data type or specify in Python d type equals float 64. Okay. So this is just specifying the data type of using 64 bits rather than the default 32 for a float. And of course we want to use formulas that would produce truncation errors O of h squared, which certainly will be true for the central difference, but also those second order forward and backward formulas that we derived that required more functional evaluations, remember, than the previous versions that were uncentered. So either way, we want O of h squared truncation errors. So on problem 6 on page 196 of the textbook, the idea is to use a finite difference approximation of order h squared accuracy to compute the derivative of a function at the value 2.36 and the second derivative at 2.36, where the data is given in this very small table here. So for these values of x, we have the corresponding functional information. Now, what's really interesting is that notice that the data that's presented to you is, for these x values, you're given this data of a function. Do you really know what f of x is? I mean, this simply is the problem as it's stated. You might be thinking, well, wait a second, they didn't tell me what the function is. We don't need to know the function. All we need are appropriate functional evaluations that can be used to approximate those derivatives. So we don't really need to know what f of x is at all to estimate the derivative, which makes this approach, this FDA approach, very powerful. Then one thing you'll notice is that what separates each of these values of x is the value 0.01. So that tells you something about the steps that we're taking if you go back to our formulas. Also, you'll notice that the data moves from 2.36 forward, notice that, to 2.37, 2.38, 2.39. We're not going to be able to use any values to the left of 2.36 because we weren't given any functional evaluations there. Right? So if we move on to the next slide, we'll see that, all right, if we're going to use this particular data to approximate the derivative and the second derivative at this point, we're going to use forward differences, and for the first derivative we'll need this formula, which requires 3 functional evaluations, and for the second derivative we'll need this formula, which requires 4. Again, the coefficients that match certain increments of the functional evaluations come from those tables, right? And you can always just look at those tables to decide on how to specify the formula. And so again, if this represents f of x, this is x plus h, this is x plus 2h, notice it's evenly spaced, and this is x plus 3h. Clearly h is equal to 0.01. That's the difference between all of these x values there. So f of x plus 2h in this case would be this particular value, 0.86710. It would go in there, and this would be 4 times f of x plus h, which would be this value here, 86289, and so forth. So you can plug in those values, and if you do that, you would be able to show that the derivative would be approximated by this value, 0.424, and the second derivative would be negative 0.200.